Today in this video we are going to discuss about van der Waals equation for real gas. Actually in the previous it is the continuation of gaseous state. Actually in the previous video we have discussed about the compressibility factor jet. Now it is a van der Waals equation for the real gas. Now till now so far we have discussed about ideal gas equation, which is PV is equal to nRT. What is ideal gas equation? Which is PV is equal to nRT. What is ideal gas? All these things I have discussed in the in my previous videos. Here ideal gas means which obeys all the gas laws and the ideal gas equation at all conditions of temperatures and pressure. And I told you already, there is no such gas which obeys all the gas laws and the ideal gas equation at all conditions of temperatures and pressures. So actually real gas behaves like an ideal gas at low pressures and high temperatures. Actually real gas behavior is completely different when compared to the ideal gas. Real gas behaves as an ideal gas at low pressures and high temperatures. Now here there is an equation given by the scientist van der Waals. Actually many equations are proposed for this real gas equation, but the successful one is by the van der Waals, which is given by here P plus A n square by V square and V minus NB is equal to nRT. This is the equation given by van der Waals for the real gas. This is for the ideal gas and this is for the real gas. Now here, before going into this van der Waals equation, I would like to discuss about the two postulates from the kinetic theory of gases. And the first, the postulate one is actually the postulate or the whatever it may be assumption you call. So here now the first assumption, here there are many postulates in the kinetic theory of gases. Now I would like to discuss about only two assumptions which are not applicable for the real gas. And the assumption is there is no forces of attraction between the gas molecules. There is no forces of attraction between the gas molecules. That was one of the assumption in the kinetic molecular theory of gases. Here, this is why I am saying it is not applicable for the real gas. Means here, when there is no forces of attraction between the gas molecules, there is no liquefaction. There is no liquefaction upon cooling. But if you observe the gas molecules, for example, you take simply water in a container, a closed container, and externally you are supplying some amount of heat. What will happen? By absorbing that heat, here this water will boil, and here the liquid vapor will be converted into the water vapor. So if you remove this temperature, means if you remove heat from the outside, what will happen? Means upon cooling, here these gas molecules, whatever the vapor, water vapor is there, slowly here liquefies. Here means these vapor molecules will be converted into again water. So here, if there is no forces of attraction between the gas molecules, there is no liquefaction of gases, but there is a liquefaction of gas now we are observing. So here, whatever the postulate given in the kinetic theory of gases, there is no forces of attraction between the gas molecules. This is not true for real gas. This is not true for real gas. So here real gas molecules have some forces of attraction between them. So here if the forces of attraction is not there, means here force is affecting means here what is the term affecting here? Force per unit area. How you will measure the pressure? When the gas molecules are taken into the container and when these are moving, when these gas molecules strike the walls of the container per unit area, when they strike with some force, when they strike the gas wall of the container with some force, per this unit area, For example, here the gas molecule in the container is striking the wall, and the wall area, this is per unit area. So force per unit area is nothing but pressure. Got my point? So here, when there is no forces of attraction, means what is the term affecting here? It is the pressure affecting here. So we have to correct that pressure. What is the correction term from the first assumption? It is when there is no forces of attraction, the pressure term should be corrected in the ideal gas equation. So what is the corrected term? A n square by v square. Why they have written a n square by v square, that all will discuss later. Here, what is the term it is affecting? It is pressure it is affecting. So it is the assumption from the kinetic molecular theory of gases. Based on this assumption, this assumption is not true for real gas. This is applicable only for the ideal gas. So here the next term, what is the correction term next? Volume term. And now I am going to discuss about another assumption made by the kinetic theory of gases. This is the second assumption. First assumption, there is no forces of attraction and between the gas molecules. I have told you already. I think this point is clear to you. And the next point is here. Next assumption from the kinetic theory of gas molecules is here. The volume occupied by the gas molecules. The volume occupied by the gas molecules. The volume occupied by the gas molecules can be neglected compared to the volume of the gas. Volume occupied by the gas molecules. Here, underline these two terms. Volume occupied by the gas molecules and the volume of the gas. The two terms. What is meant by volume occupied by the gas molecules and the volume of the gas? These two terms should be clear before going into this topic. So here, volume occupied by the gas molecules. Volume occupied by the gas. First we'll discuss what is volume of the gas. Volume of the gas is nothing but here whatever the space is available for the gas molecules for their movement is the volume of the gas. Got my point? Whatever the space is available for the movement of gas molecules is nothing but the volume of the gas. Okay. Now, what is the volume occupied by the gas molecules? Here, try to understand clearly. This volume of the gas means here, whatever the space is available for the movement of gas molecules is the volume of the gas. For example, that depends upon the container. For example, if you take this container and you take these gas molecules, this is the space available for the gas molecules. That is nothing but the volume of the gas. Okay. Now, volume occupied by gas molecules. Here, now, these gas molecules, you collect one by one, whatever the, just assume, you collect whatever the gas molecules are there, you collect, and here, try to arrange these gas molecules in a container. So, this much space is sufficient for the arrangement of all these gas molecules. This is this one term, volume occupied by the gas molecule. Actually, volume occupied by the gas molecules is this much. Here, are you getting my point? But if you take these gas molecules into the free space, they will move in the container. That is nothing but the volume of the gas. Now the postulate or the assumption made by the kinetic theory of gas is that volume occupied by the gas molecule is neglected compared to the volume of the gas. So here, when compared to here, this space can be neglected when compared to this volume. Okay, here because the gas molecules are assumed to be of point masses, when compared to the volume, this entire volume, this area can be neglected. So here the volume occupied by the gas molecules can be neglected when compared to the volume of the gas. What is the volume of the gas? It is the free space available for the movement of the gas molecule. So if I ask you what is the volume of the gas, if I ask you at this condition, if I ask you what is the volume of the gas, here you can say volume of the gas is exactly equal to volume of the container. Because when compared to this volume, this can be neglected. So what is the volume of the gas? Volume of the gas is nothing but volume of the container. Okay. This is true only for the ideal gas. Because the ideal gas molecules are of point masses. Whatever the space occupied by the gas molecules, that can be neglected. But this is not true for the real gas, because real gas molecules are rigid spheres which occupy some volume. If you want to explain, now for the real gas I am asking, what is the volume of the gas? Here these occupy some space. Here now what is the volume of the gas? Whatever the free space is available for this gas molecules is nothing but the volume of the gas. But here they do occupy some space, and now if I ask you what is the volume of the gas, here volume of the gas is not equal to volume of the container. So if I ask you what is the volume of the gas, you will say, ma'am, here the volume of the gas is volume of the container minus this area. Means volume of the container minus volume of the molecules, volume of the gas molecules. Then only you will get this area. Are you getting my point? Volume of the gas means whatever the free space is available for the movement of gas molecules is the volume of the gas. Here this is the volume of the gas is equal to volume of the container in case of ideal gas. This is not true for the real gas, because ideal gas molecules are of point masses, but the real gas molecules, they are rigid spheres, they have some volume. So here you cannot neglect this volume if you want to say what is the volume of the gas. Clear? Now, what is the second correction term in the ideal gas equation? It is the volume term should be corrected, because here the real gas molecules are the rigid spheres, they occupy some volume. What are the two correction terms in the ideal gas equation, in the real gas equation given by van der Waals? One is pressure correction and the second one is volume. Here this volume we call as the excluded volume, because we are excluding this volume while we are saying what is the volume of the gas. Clear? Now we'll discuss these 2 points clearly. Okay? Now the first term we have to explain is the pressure term, pressure correction in the van der Waals equation. Now let us consider an ideal gas and real gas too. Now here what is our first assumption made by the kinetic theory of gases, which is true for only ideal gas, not for real gas? That is, there is no forces of attraction. So when there is no forces of attraction, that is not true for the real gas. Okay, and here how the pressure term is affected. So here these are the gas molecules, it is in the case of an ideal gas. So how we'll write the pressure? When the gas molecules are here, when they are moving, they collide with each other, and also they will collide or they strike the wall of the container. They strike the wall of the container. So whatever the pressure exerted by the gas molecules per unit area is the force per unit area, which is nothing but pressure of that particular gas molecules. This is for ideal gas. Okay, now come to real gas. Here these for example, this is the real gas molecules which is going, and you just assume, which is going and want to strike the wall of the container like this. Okay, but here it is a real gas. They do have some forces of attraction. FOA means forces of attraction. So here real gas molecules are having some forces of attraction. So when this among the n number of molecules, here you just assume one gas molecule, real gas molecule, is exerting some pressure by striking the wall of the container. So here it is, here these gas molecules, whatever the gas molecule is at the wall of the container, it experiencing an inward drag or inward pull from the other molecules. Because why? Because here there is a forces of attraction between the gas molecules. So these gas molecules, let's just assume it is a gas molecule X, and here it is a Y which is attracting this gas molecule X, and so it is experiencing some inward pull. So what will happen because of these forces of attraction? Here it cannot strike the wall of the container with more force as the ideal gas molecules do. Got my point? Here the ideal gas molecules, there is no such forces of attraction, there is no inward pull or drag it is experiencing, there is no drag or inward pull experiencing. But here this real gas molecule, here it will strike the gas of the wall of the container per unit area, force per unit area, that is the pressure exerted, we calculate. But here it is because of the forces of attraction, it is experiencing some inward pull. So whatever the pressure exerted by the ideal gas, it is greater than the pressure exerted by the real gas. Got my point? Now here, although in addition to this point, here there is a forces of attraction. So here when there is a forces of attraction between the gas molecules, they do exert some pressure internally. So here whatever the pressure we are calculating, pressure of the for the real gas, that is not completely the pressure experienced by these molecules, because here it is the pressure, whatever pressure it is exerting here. So pressure of the real gas, total pressure of the real gas is here pressure exerted when the real gas molecules strike the wall of the container, plus there is an internal pressure also, pressure internal. There is an internal pressure because there is an forces of attraction between the gas molecules. So whatever the pressure we are calculating, pressure when the gas molecules strike the wall of the container, that is not the complete pressure. The total pressure is pressure. This is the pressure when they strike the wall of the container, and the gas molecules will experience some internal pressure, that is pressure internal. Now we have to calculate what is internal pressure of the gas molecules. Why here pressure plus internal pressure? Because it is a total pressure. Got my point? Clear? Okay. Now here I have told you it is the molecule X, and here it is, these are the molecules which are pulling back these molecules are Y. There are many number of X molecules and there are many number of Y molecules, but X and Y both are same. Now here the concentration of molecules, whenever you are calculating the concentration term is number of moles given by volume. Number of moles by volume. So which is equal to N by V. Now the concentration of X type of molecules is proportional to N by V. And the concentration of Y type of, here you have to remember one point here, X can behave like Y and Y can behave like X, because these are the same gas molecules, but here this molecule want to strike the wall of the container and another one is pulling it back. So X place Y can be there and in Y place X can be there. Got my point? So here concentration of X molecules is proportional to number of moles per unit per volume, and here also concentration of Y type of molecule is also proportional to N by V. Okay, now whatever the pressure, internal pressure, that is proportional to the pressure, internal pressure is proportional to N square N by V into N by V, because the internal pressure is because of these two molecules. We are considering the forces of attraction. So pressure internal is equal to, it is because of this X type of X molecules and Y molecules. So pressure internal is equal to N by V into N by V. So proportionality is replaced by a constant A, N square by V square. Okay, now the correction term in the van der Waals equation. Clear to you? Here, as there is no forces of attraction between the gas molecules in case of ideal gas, so the ideal gas molecules will clearly go and freely go and strike the wall of the container. But here, as we are considering the forces of attraction between the gas molecules in the real gas, here when this molecule, you just assume one molecule, when one molecule want to go and strike the wall of the container, so another one, because of the forces of attraction between these two, this one pulls this molecule back. So there is experiencing molecule X experiencing some inward pull. So the pressure exerted by these gas molecules will be less when compared to this one. And also point number 2, as we are considering the forces of attraction, there is a forces of attraction between these gas molecules and they do exert some pressure which we call as pressure internal. So if we want to say the total pressure, that is the pressure which is exerted, when the gas molecules strike the wall of the container, plus internal pressure also we have to add. So here, what is the internal pressure? Internal pressure is can be calculated by here. What is the concentration? Concentration is given by number of moles per volume. So concentration of how many number of molecules are there? So here concentration of number of molecules is proportional to N by V, and concentration of Y molecules is proportional to N by V. So internal pressure is because of the number of molecules present internally in the container, so which is proportional to N by V into N by V. Proportionality is replaced by a constant A, and this A is van der Waals constant given in the equation. Van der Waals constant. Clear? This is about the correction term, pressure correction term in the van der Waals equation. Now we'll discuss the volume correction. Now volume correction. I told you already, here the volume occupied, the postulate is the volume occupied by the gas molecules can be neglected when compared to the volume of the gas. This is only true for ideal gas. But the real gas molecules, here the volume of the gas is not equal to, this is the space occupied by the real gas molecules. This is in the case of real gas. It is the space occupied by the ideal gas molecules. This is in the case of ideal gas. Here, the volume of the gas, if I ask you what is the volume of the gas, it is equal to volume of the container. So volume of the gas molecule, here volume occupied by the gas molecules can be neglected when compared to the volume, this volume. This is true for ideal gas, but here real gas molecules are rigid spheres. They occupy some volume. So what is the volume of the gas now? Volume of the gas is equal to volume of container. Volume of the container minus what is the volume of the gas now? You just tell me. Here this is the volume of the gas, because what is the volume of the gas? Whatever the free space is available for the movement of gas molecules is nothing but volume of the gas. Whatever the free space is available here, this is the volume of the container minus this volume gives you the volume of the gas. Okay, what is the volume of the gas? Volume of the container minus this volume. So volume of the container minus volume of the gas molecules, or volume occupied by the gas molecules. Occupied by gas molecules. So volume of the gas is equal to volume of the container minus, this volume we call it as an excluded volume, because we are excluding, we are removing this one, excluded volume. This is excluded volume. In some textbooks it will give excluded volume. So here volume of the container minus, here volume occupied by the gas molecules. Here the volume occupied by the gas molecules is represented by the letter B. This area is B. So volume of the container minus volume occupied by the gas molecules. So it is V minus B. For n mole of a gas, for n mole of a gas, volume of the gas is equal to V minus NB. So the second correction term is V minus NB. Clear? Now the van der Waals equation is given by P plus A N square by V square, correction term, pressure correction term, and volume correction term V minus NB is equal to nRT. Now you tell me what are the terms in this. P is the pressure of the gas, and N is the number of moles, V is the volume, and here V is the volume, and N is number of moles, and here A and B are van der Waals constants, N is number of moles, R is universal gas constant, and T is absolute temperature. This is real gas equation given by van der Waals. Repeat with me. P plus A N square by V square, V minus NB is equal to nRT. That is real gas equation given by van der Waals. Okay, here I told you clearly it is the case of ideal gas and it is the case of real gas. Volume of the gas is equal to volume of the container. Here we have to remove this volume, because to get the volume of the gas, here as we are excluding this volume, we are subtracting that volume. For n mole of a gas, it is V minus NB. Okay, clear? This is about the van der Waals equation. Okay. Guys, if you want me to explain any topic or any unit, just ping me in the or write in the comment section. I'll post a video immediately based on that topic. Okay, bye.